In the last video, we developed the Impulse-Momentum Theorem and used it to estimate hammer-hit type forces that would otherwise be hard to estimate. In this video, we're going to go for the more commonly used application, which is conservation of momentum. So to this end, I need to better define a couple terms. We'll first start by defining a system. And this is going to be a collection of particles under study. And then we'll define an isolated system. So this is a system where the external force acting on it is 0. Yeah, right, I can spell. There we go. So just to kind of clarify here the forces that count and the forces that don't. So the beauty in physics is we can just go ahead and take any old collection of particles and say, hey, that's my system. And then I can go ahead and draw a box around them or something and say, I am looking at the three of these particles combined. So then the idea is, if I want to define the external force on the system, that would be due to forces that are external to the system acting on the individual particles. So this might be the external force acting on particle 2, external force acting on particle 1. This could be, say, gravity from outside the system, an electric force from outside the system. The key thing is these are not interactions from particles 1, 2, and 3. And maybe this would be the external force acting on particle 3. I can just say the external force acting on my system. Turns out you can just write that as the sum over all of our particles of the external forces acting on each of our particles. So this would be the external force acting on particle 1 plus the external force acting on particle 2, etc. Okay. What doesn't count are the internal forces. So for instance here, there might be some interaction between, this might be, oops, let's choose a better color. That one. This might be the force acting on particle 1 due to particle 3. This would be the force on particle 3 due to particle 1. That would be equal and opposite because they're an action-reaction pair. We could have something similar. Say this might be the force on particle 1 due to particle 2. This would be the force on particle 2 due to particle 1. They're a different action-reaction pair. And then finally, this might be the force on particle 3 due to particle 1, and that would be the force of particle 1 on particle 3 on 2 due to 2 due to 3. Yeah, there we go. And that's also an action-reaction pair. Now it turns out, since the action-reaction pairs are always negatives of each other, even if you were to add them in, they would cancel out. So internal force pairs don't count. And we've never worried, when we've looked at anything before, we've never worried about the details of the forces that hold the system together. And that continues to be true even for systems where the object, even for systems where there's clearly distinct objects. Because if you think about it, even if you look at something that seems like just a single object like a ball or something like that, that ball is made up of a few gazillion atoms, right? and we never worry about all the forces between all the atoms that hold the ball together. So we've already been doing this for quite a while. It turns out that for any system, we can define the momentum of the system, p tot, it turns out to just be the sum of the momenta, p2, of the particles. So you just particle by particle find the momentum, add it up. They're vectors, so you will have to take your x and y components separately, but the total momentum of the system is just the sum of all the momenta. Now here's the kicker. If the system is isolated, then that means that the external forces acting on it are zero, so F net is 0, which means the impulse acting on the net impulse on it is also 0. And by the Impulse-Momentum Theorem, that means the change in momentum is also 0. So the way we can put this is to say that the total momentum after the collision, so final, is equal to the total momentum before the collision, so I initial. And this is really super helpful because, say if you're looking at a collision between two cars, for example, normally in order to model it all, you would have to do a hideous numerical simulation trying to estimate where all the atoms of the cars end up at. And this is indeed what automotive manufacturers do when they're designing their vehicles to get some sense of their crashworthiness, because they need to understand how the vehicle deforms. But if we don't care about how the vehicle deforms and we're only interested in how fast things are moving afterwards, then we can just exploit this fact that the total momentum afterwards is equal to the total momentum initially, and away we go. So let's start doing some examples of this. We'll start first with what I like to call a sticky inelastic collision. Now, we'll have to define energy to properly talk about elastic versus inelastic. But suffice it to say right now, for an inelastic collision, the hallmark of one of those is that there's deformation or heat or sound or something. So we can go ahead and take a look at one. For instance, let's say I've got a car here, and these speeds are race car speeds, so barely realistic. Let's say 500 kilograms, 200 meters per second to the right. And let's say that we have a car here. We'll say its mass M2 is 1,000 kilograms. And we'll say it's going to the left at V2 equals negative 200 meters per second. So you'll already notice that the way I'm handling the signs here, I'm handling them the way we handle signs in kinematics versus the way we handle signs in forces. And I find that when we're doing things in one dimension, at least personally for me, that's the way to go. So in other words, I'll handle all the is it moving right, is it moving left when I substitute in the numbers, not when I'm setting up the letters of the equation. So anyway, this is the before situation. Now let's go take a look at after. After, we have a big twisted mass of metal, and we know it's skidding off to the left. And we know the mass of the twisted mass of metal M has to be M1 plus M2 from before, so that'll work out to be 1,500 kilograms. So, all right, we would like to know how fast is the thing going. Well, here's what we can do. You ask yourself, is there a way that I can put the two objects I care about, because when they collide, there's going to be horrendous contact forces I don't know how to model. I need to make them internal. Can I make them internal? Yes, you can, by cleverly defining your system to be the pair of those. Next question, is it isolated? Well, there is a normal force in gravity acting on each car, but because the surface is horizontal, the normal force and the gravity are equal and opposite, so it all adds up to 0. So yes, the net external forces on the system add up to 0. So we've got both of those caveats out of the way, so that means I am allowed to say that the total momentum, final equals the total momentum initial. And here, since all the action's happening in just the x direction, we'll just take a look at the x. So this will be P final, so equal P1, P final x, that equals P1 initial x plus P2 initial x. All right. So looking at our diagram here, this is going to be m times v final. And yes, we know from our horse sense it's moving to the left, but because we're treating the variables like we were doing it back in kinematics, where we'll let the signs take care of themselves at the numbers stage, we just put in f, and we keep in mind that when we solve for it, it better be negative. Similarly, P1 initial x is going to be m1 v1 plus m2 v2. And yes, we know this one's going to, the object 2 is going to the left, but we'll worry about that when we put in the number, not before. Okay. So we can find the final speed, final velocity of the twisted mass of metal. If I divide both sides through by m, I get m1 v1 plus m2 v2 over m. All right, let's put in the numbers. So 500 kilograms times, we said it was 200 meters per second, plus 1,000 kilograms times negative 200 meters per second. And we're choosing the negative because we're going to the left. And we'll divide that all by 1,500 kilograms. So, alrighty, that's going to be 1/3 of a 200. Yep. That will get you negative 67 meters per second. And again, we interpret the negative as meaning that the twisted mass of metal at the end is also heading off to the left after the collision. Now you may wonder, why didn't we worry about the force of friction? Surely the wheels are skidding as the drivers have locked up their brakes and everything. Yeah, sure, but if you're looking at the split second before the collision, the split second after the collision, the force hasn't really had any time to act. And so as long as we're looking immediately before and immediately after the collision, we can ignore the effects of friction here. Okay, so that's one case. So here we started out with 2 particles, we ended up with 1, and it's just when you do your sum, however many particles you have at that particular time, you just add up all the momenta and equate. So let's do another example. Let's go take a look at a bouncy inelastic collision. So here, this would be a case where we end up with the same number of particles that we started with. So again, let's have our same two cars collide. So this is M1, it's still 500 kilograms. And we'll say V1 initial is 200 meters per second to the right. Here's car number 2. M2 is 1,000 kilograms. V2 initial we'll say is minus 200 meters per second. And again, the minus is because we're going to the left. Well, we know here with equal speeds, we know from our intuition that the big car is going to win. Both cars at the end of the collision are going to be moving to the left. So let's say that the big car winds up exiting out at V2 final equals minus 20 meters per second. We would like to know when the first car bounces off, we know from our intuition it'll be going to the left. We'd like to know what V1 final is equal to. Again, it's the exact same idea. We can go ahead and conserve momentum in x and y here. Sorry, in x. So we can say P final equals P initial. For this is our total momentum. Take the x component. That will be, oops, forgot to draw that car going to the left there. That'll be, let's see, P final will be equal to P1 final plus P2 final, all acting along x. I'm not going to bother writing the sub x anymore. This will be P1 initial plus P2 initial. Alrighty. So we can go ahead and write that out. This is going to be M1 V1 final equals M2, whoops, sorry, plus M2 V2 final equals M1 V1 initial plus M2 V2 initial. And what we were being asked to solve for was V1 final. So we can rearrange a bit. So here we're just doing algebra for a sec. So M1 V1 final equals M1 V1 initial plus M2 V2 initial minus M2 V, oops, sorry, minus M2 V2 final. Now I can divide through by M1. And if I group things around a bit, I get V1 final equals, divided by M1 on both sides, this will just be V1 initial, plus here I could combine these two terms by pulling out an M2. So, and then after I divide by M1, I would get M2 over M1, V2 initial minus V2 final. All right, and then it's just a matter of sticking in the numbers to see what we get. So we said that V1 initial was 200 meters per second, plus this will be 1,000 kilograms over 500 kilograms, times we said V2 initial was negative 200 meters per second, minus a negative 20 meters per, oops, here, let me write that onto the next line, minus a negative 20 meters per second. Make sure to keep track of your signs. This minus sign here is because the thing's going to the left. This minus sign is just because I'm subtracting the two things. But all right, so let's see, this is going to be 100, negative 180. We're going to be timesing by 2, so that's negative 360. We're going to add 200 to it. That leaves me with negative 160 meters per second. So that first car is going to bounce off to the left at 160 meters per second. You can also do this kind of a trick for explosions. An explosion would be an example where you start with, say, one object and then you end up with two, as an example. So it'd be just like when we did the sticky collision here. Instead of starting with two particles and ending with one, you start with one particle and end with two. There's one other trick you can look at, and this is sometimes you can look at a system that's what's called partially isolated. So an example of this might be, let's say you have a 1 kilogram cart that's moving down the track at, let's say V1. Initial is 10 meters per second. And then when it gets right here, a blob of putty that was also 1 kilogram falls down and lands on the cart. Afterwards, when the putty sticks on the cart, I would like to know what is the final velocity. So here you can ask yourself, is the system isolated? And the answer is absolutely not. The system is not isolated in the y direction. And this is because if I were to make the cart and the putty my system, for the cart, yes, I will have gravity down, normal up, they cancel, no net force there. But first we'll have gravity acting all by itself on the putty, which means that the net force on the system, for even a part of it, and only needs to be for a part of it, is non-zero. However, gravity is only acting in the y direction. The net force on the system, so keep in mind we're making the putty plus the cart my system. The net force on the system in the x direction is 0. So that means the system is isolated in x but not y. So what this means is that momentum is conserved in x but not y. So this means we are still free to conserve the x component momentum. So we can say that p tot x, or sorry, p tot final, p tot x final equals p tot x initial. So this will be the initial is going to be the mass of the cart times V1 initial, and since the putty was moving purely vertically, there is no x component momentum due to the putty. And afterwards will be equal to the mass of the combined system, which would be the putty plus the cart, which is now 2m, times V final. Cancel, cancel. You get that V final is 1/2 V initial, so it's 1/2 of 10 meters per second. So after the putty lands, it's going at 5 meters per second. Okay, in the next series of videos, we will be continuing to explore momentum conservation. Catch you on the flip side.